So welcome to this lecture on advanced digital system design in the course digital system design with PLDs and FPGAs. In the last lecture we have looked at the VHDL coding of the finite state machine or controller. Basically we have looked at the various ways you can code it, code the FSM, and we have shown some simple example to illustrate that coding styles. There are various ways and some schemes have certain quirks or trouble it brings, like synchronous reset. We have handled that situation, and today we will continue with the issues with the finite state machine, but before that we will have a quick run through the last lecture slide to be in sync, because that may be useful even in this lecture. So let us turn to the slide of the last lecture. So here we have looked at the block diagram of the state machine, a 3 block diagram. We have first looked at this and we said these inputs, clock, reset and output. Definitely clock and reset normally come from outside, so they can be ports. Sometime if it is internal it can be signal, but input and output, if you are testing it standalone then it is port. But many times when you are integrating with the data path, it could be ports or signal. Maybe some input is coming from outside, so that could be port. And very important thing, though we said that you can adopt various ways of coding the finite state machine, you have to choose the style as prescribed by the specified by the synthesis tool. The basic idea is that synthesis tool should be able to infer that this constitute a finite state machine, so that the FSM specific optimization, the problem solving can be done on this structure. Otherwise if you just code this as a logic and this as flip flop and this as logic, then the implementation would be correct, it will work perfectly, but the synthesis tool will not be able to do any FSM optimization, or any issue it can normally solve it cannot be done. The example is that we have talked about the state diagram optimization. Unless the tool infer that it is a finite state machine, the state diagram optimization cannot be done. There will be redundant states, unnecessarily wasting area in the next state logic and output logic and so on. Okay, and we have looked at the various ways, and here in this 3 block we could have this written in a process, this in a process. This can be written in a process if the number of outputs are greater than the number of states. It can be a concurrent statement if number of outputs are much less compared to the number of states, because then there are only 2 outputs, you need only 2 concurrent statements. But suppose there are 7 states, you may end up writing a case with 7 when wherein only 2 outputs are specified. Not very kind of concise coding, though the hardware wise it makes no difference, but it's a long code. That's why I said you can write concurrent statement. We also said that you can combine these two in a single process, because the in VHDL you can specify a set of registers with the preceding logic in a single process. So that can be done. In that case you have a process for these 2 blocks together, and with a process or a concurrent statement, set of concurrent statements for output logic, and you can include the asynchronous reset here along with the flip flop. If it is synchronous reset, it is included here, and when you combine, as I said, when you combine both together there is an issue. We have discussed that. I will just throw light on it. And we also said normally when you code the next state logic, we write a process with the present state as input, and in the sensitivity list, and all the inputs, because these 2 are the input to the block, and we say case present state is, and for each state we specify the transition using if. Okay. Similarly for the Moore kind of output, you can say case present state is or with select, whichever one you use. Again you can use if for the melee output under the case and so on, and this is a process where use the if statement with the reset and clock event or rising edge clock for the flip flops. Okay. The next possibility is that we come to a 2 block view where the next state logic and output logic is combined into a single block where the outputs are next state logic and the outputs. So now you can write this in a single process and a flip flop in a process, and flip flop is as usual, but here again you do a case present state for each choice. You specify the output if it is Moore output straight away, and melee then you can write an if then kind of structure, and for the transition under each state for each when statement of the case you can specify the transition, various transition using the if. So one advantage of writing this way is that when you have a state diagram, like quickly looking at the state diagram, you can complete the whole logic in one shot. Okay. So that is one advantage of writing it together, but if you write as in early, then when you write the next state logic coding you have to keep the state diagram, run from top to bottom, then again come back, write the output logic, and top to bottom you write, and when you debug if something goes wrong, depending on where the trouble is, you have to go through both code. Okay. I mean these things are come with experience, and for some it occurs naturally. Those who are very systematic, sometime by their habit they stumble upon these kind of advantages, but then it all shows that you need some kind of planning experience, because even writing the code, though they are equivalent, some style of coding is helpful in a quick kind of design, debug and things like that you should keep in mind. And we have looked at the problem of a sequence detector mainly as an exercise, not as a serious kind of design. I don't think you need to use an FSM based sequence detection in communication. Okay. You can do better than that, you can do much simpler schemes than doing this, and we said it's an overlapping detector. That means like in the case of 101, you have a 01 here, then the 3, 4, 5 also form a detector, sequence detection, and we have seen the kind of the state diagram and we have seen the coding. The main thing is that the library entity and the most tool allows you to define an enumerated kind of data type for this and define the present state and next state as that type. Then you write a process for next state logic with the present state and inputs. In this case only one input is there, inputs in the sensitivity list. Then you go state by state. Case present state is when A, then you use if on that to specify the transition. Important thing is to do all the transition, if else everything. Don't think that because you are in state A you don't need to say else next state A, that will cause implied latch. So you continue through, and the flip flop is like an asynchronous reset. You know how to write that. If reset, then present state is starting state, or upon the clock present state get next state. And when you write the output as a concurrent statement, you can use when else or with select. If it is with select, you say with present state select, or with when else, you can write like that. And we have seen the next state logic and output logic together. Only difference is that in the case of each choice of this present state, you specify the transition as well as the output, okay. And when it is Moore there is no condition on it. When it is Mealy you can write a simple logical condition here if it's simple case, or you can use if or case or whatever is a appropriate thing to use at that point in time. The flip flop is same. Then we have seen a Mealy kind of machine for the same problem, and we have combined the next state logic and output logic, and you can see that the detect here is written as a Mealy type. Detect gets D in, that means if D in is 1 detect is 1, else detect is 0. And many a times when you can write it in a very straightforward kind of logic, it is better to write like that. Sometime what happens is that people get used to this syntax, and even for simple things like this one tend to write the if, saying that if D in is 1 then detect is 1, else detect is 0 and all that, and forget all about what could be the hardware. It is nothing, detect it here it's a decode of C which is in our case maybe Q1 bar Q0. So in this case in the Mealy machine we are combining the next state logic and output logic in a process, and the code is similar. Only thing is that we have this detect which is written as a part of detect as a function of D in. So when you decode it is like the state C and D in is the detect. So it is Q1 bar Q0 and D in, okay, and it's better you remember these basics always. What happens is that when one danger with the more and more sophisticated tools and these kind of languages, that you tend to forget or tend not associate the hardware with it, and people like I have seen students writing this simple thing as if D in is 1 then detect is 1, else detect is 0 and so on, and forget what is the hardware. It's not a good thing. I have asked some students what is that hardware, what does it what does the synthesis tool generate. If you write a statement like that, then they are sometime at loss even with some very trivial silly stuff. So wherever you can bring clarity by making things simple, you should make it simple than use all the if, case and nest it and things like that. Though we are learning about it, wherever things can be made simple, elegant, you should do it. And if the same thing is written as a concurrent statement instead of this, if you are writing it outside, here we are combining both next state logic and output logic together. But if it is outside, then you can write like this: detect is 1 when present state equal to C and D in equal to 1, else 0, okay. So you can write like that, and here to write with select is difficult because you have 2 inputs. If you are kind of adamant, then you can do that. What you can do is that you have to kind of group present state and the D in together into a temporary signal, then you say with that signal select and put this value and so on, okay. But with again it is tough with an enumerated data type, because here we are using some kind of symbolic assignment, and here it's a numerical value, and though ultimately it will all be converted to standard logic vector and so on, it is difficult at least to do the with select. So no harm, because you are specifying both the mutually exclusive condition, so there won't be any priority, and this will result in a simple logic. Then comes the synchronous reset along with when you write the next state logic and output logic together. If it is alone, next state logic alone, there won't be problem. When you combine, you can make a mistake in the sense that you say if reset is 1, then you say next state gets A, because that's what you want, and you forget all about the outputs, and you say else and case present state is, and you say when H0 you write the outputs, there could be 10 outputs and all the transition and so on, okay. But mind you, there is, as far as if is concerned, there is one choice here and the kind of mutually exclusive choice here. Underneath the case com, there the output is specified and here it is not specified, so you get an implied latch for the reset is equal to 1. It is dangerous, so we have to say output is some value. So don't care is one kind of, because this say when the reset is getting kind of asserted for that duration. So you can even make it inactive, you don't have to say don't care, you can make it the inactive value to be very sure that during when reset is 1 you don't get any nasty surprises, but it's improbable. So that is one way of sorting this out. Another way of sorting it out is that write the if just for this and you say end if, okay, and write the case separate, okay, separate it out. So if reset is 1, the next state is a end if, because we are not combining it, there is no else here. So like that you do and do the case present state is. As I said, I don't prefer this because this looks as if there is no else kind of thing, so it could be problematic. So don't write like that, better to write like this. And we also said normally if you don't specify anything, like you just leave the code like this, and then the tools will assign a symbol kind of encoding, mostly sequential encoding, like this will be 0, 1, 2 and 3, okay. And if you want to kind of, for whatever reason, and we are going to see what reasons you could there could be to change this assignment, but then if you want it you can use the kind of predefined attributes of the VHDL to control that. That is called state encoding, sequential gray 101, 100, and this I am showing what was supported in the integrated system environment of the Xilinx ISE or ICE, okay. But I have seen that the attribute in the recent tool like the Vivado of the Xilinx, this attribute is changed. So please check which tool you are using and refer to the vendor manual for the appropriate attribute. But more or less maybe some name changes, but more or less the syntax is same. So here the syntax is saying attribute state encoding of whatever state you have given the name for that enumerated data type. So type is gray or sequential 101, 100, and we will see what is 101. Yesterday I said what is it, and then you get what the encoding defined by this. But if you want a very specific encoding, you can use attribute enum encoding of state type, then you can literally say what is the encoding, okay. And if that is not possible, you could, instead of you can forgo the kind of enumerated data type, and you can kind of hard code the present state and next state into vectors, standard logic vectors, and you can define constants so that you don't need to change, like if there is a change in the state diagram, then if you write numerical values in the VHDL code, you have to go and change everywhere, it is error prone. So you can define constants for each state with the proper state assignment, whatever is assignment, then you can implement that code. Then if there is a change need to be done, it need to be changed only in one place. You can add more state, you can change the state assignment, you can remove the state and so on in one place, okay. Definitely the code also, if you add and delete, you need to change in the VHDL code, but minor changes in the state assignment, you don't need to change anything. And I also said about FSM editors, there are graphical tools which allows you to draw the state diagram and which will create the equivalent the code VHDL or Verilog, there is no magic in it because it is one to one, and it as you draw it, as you put various elements, it knows the moment you put a bubble, it knows it's a state, and a arrow it's a transition. So that is kept track, and ultimately in some data structure, and ultimately some template codes are generated. It's not very difficult, as I said. If you are I mean, it can be done very easily, only you need to be good in programming. So that is what we have discussed in the last lecture. I have gone through this so that again that gets into your mind properly. Now we will continue with, we have actually in the earlier lectures we have looked at certain issues with the finite state machine. If you remember, we have looked at how to do the state diagram optimization. Okay, what is the basic idea, what are the equivalent state and which are redundant, how to detect that from the next state logic and output logic and so on. And we have also looked at the output races when there is a kind of multiple flip flops change state at the same time. Owing to the difference in propagation delay, there could be transitory states, and if these states produce output, that could create problem in the circuit. So how to handle that, and we have looked at the gray coding, output registering, and we mentioned about the VHDL coding for that. Then we looked at the transition table. If we choose the various type of flip flops, basically D type, T type and JK type of flip flops, and we have kind of discussed what are the maybe the advantage, disadvantage and so on. So let us continue with the state assignment. Okay, so let us take that part today. So remember that you have this state machine where the next state logic, output logic is there, and we have the state, sorry about this should come here, this Q. So we say the state machine is going through different states, and when we design we say state A, state B, state C, state D, but before proceeding with the next state table and output table, we have to assign some numerical value to it. Okay, now we are going to see whether that affect. The question is that what is the effect of state assignment on the next state logic, okay, say or output logic. Say the question is that if you do the assignment in a particular way, can the area required for implementation of this can be minimal. Okay, suppose there are 20 ways of doing the state assignment, in at least in one of them or multiple of them the area is half of the maximum. Okay, then it is better to choose that particular state assignment. Okay, and that is natural because at least for the next state logic, the next state is a function of the present state and the input, and this is a combination logic. And we so you imagine the next state table, you have inputs, you have the present state, you have the next state, and we are trying to form equations of the various D2, D1, D0 in terms of the Q2, Q1, Q0 and the inputs. So you can imagine, if you are familiar with the Karnaugh map, you go to Karnaugh map, you try to group the minterms. So our question is that if you do the assignment in a particular way, you can group it such that the redundancy can be removed and this become minimal. Similarly here, because the output is a decode of the present state and the input, and if you do the assignment in such a way, then whether this logic can be minimized or there is an assignment such that both can be minimized. There is a very great saving in area. So if the area is reduced many times, the interconnecting wire length can be reduced, the delay will be less, the power dissipation will be less. So in the digital VLSI and FPGA and all that, it's very wise to kind of optimize the area or minimize the area. That will result in a lot of advantage with respect to the power with respect to the timing and so on. So that is what we are going to look. So at this point it looks like, say you work out all possible assignment and find out the area which is minimal. Okay, that's what we are going to look at it, whether that is a possible thing. So that is the idea of the state assignment. So take this case, the number of states are S. Okay, suppose we have say 5 states, then the number of flip flops for the binary encoding is the logarithm of S to the base 2, and normally you take the ceiling because this could be a fraction. Say in the case of 5 if you say log 2, it will be some 2 point something some decimal number. So we need to use take the ceiling which is 3, then we will end up using 3 flip flops. Okay. So now the question is that we are trying to kind of do all possible assignment, that is what we have decided. Okay, let us do all possible assignment. So what are the number of possible ways to do the assignment? Say we have S states, we have N flip flops. Okay, let us assign a variable to it. Instead of putting this in the expression, log S to the base 2 is N, the ceiling of it, that is N. So how many possible ways you can do the state assignment in terms of N and S? First thing to kind of decide is that whether in all these kind of counting problems you should be very clear whether it is a permutation or a combination. So every time if you have confusion, like for those who are familiar, it's one shot. Okay, if you struggle with it, the best thing to take an example of, suppose you have say 4 states, possible states like 0, 1, 2, 3. You have 4 possible states and like 2 flip flops for 4 possible state and 2 real states S0 and S1. So then you know that the first state S0 can get any of the 4. So there are 4 possibilities. Okay, and if you assign 4 possibilities, one of the 4 possibilities, then when it comes to the next one you have only 3 choices. Okay, so it's a 4 into 3. So it's a permutation because each assignment is unique, it is not a combination, like S0 getting 0 and S1 getting 1 is different from S0 getting 1 and S0 getting 0. So that alone should clarify the position. So basically if you look at the number of possible ways to do the state assignment, this permutation of 2 raised to n, because for n flip flop there are 2 raised to n kind of possible states, and S is the real number of states. So P 2 raised to n comma S. Okay, and let us take an example. There is a state machine with 17 states and not it is a real life case. There could be state machine with 17 states. So the n is 5. Okay, you will accuse me of choosing something close to the 16, but in real life it can be strange, and let us find out the possible ways of doing the state assignment. The permutation of 2 raised to n, so that is 2 raised to n is 32, 2 raised to 5 is 32, state is 17. So that is 32 factorial divided by 32 minus 17 factorial. So you have some like P n r, then it is n factorial by n minus r factorial. So 32 factorial by 32 minus 17. So it is essentially 32 into 31 into all the way into 16. Okay, and if you look at this number, it is some 2.5 some decimal number into 10 raised to 44. It's a huge possibilities. This should, that's why I put this. So if you try to do all kinds of all possible assignment and try to minimize area, it's an intractable problem. It is not going to be solved in a kind of deterministic time period. It's a for the advantage we get, the amount of computation we have to go through is tremendous. So this is not possible, like this is mind boggling. So this huge number. So this should tell you that you should not try to attempt such a thing. Okay, of course in a simple case maybe there are 4 possible state and 3 assignment you have to make, it is possible, but then when the numbers are even it looks very small, you end up with this because of this kind of the exponential way it grows. So the question is that we cannot very systematically go and solve it, but our aim is that somehow minimize the next state by doing a state assignment, okay, or by doing a state assignment minimize the output logic. So trying all possible kind of assignment and finding out the minimal is not computationally viable solution. So then in such cases when things you cannot go very kind of go through all the cases and find an optimal solution, we try some kind of sensible kind of rules which is called heuristic, that we know that if you this rule make some sense that like if you there is a basic principle which tells you that if you do this probably could be a reduction in area, and we do that. We may not get the absolute minimum, but we can be close to the minimum, or we can do better than a random kind of assignment or a sequential assignment. So we call that heuristic. So since we have the systematic method doesn't give you any solution, let us try some heuristic. So that's what we are going to do it, and we will concentrate on the next state logic minimization. So the question is that where to look for insight, okay. We want to come out with some sensible rule to apply for the next state logic optimization. Where do we look for insight, okay. Naturally the next state logic is specified in the next state table. So that is where we should look, okay. So we should look in the next state table, and now in the next state table it is composed of input, present state and next state, and next state is our for a D flip flop some D2, D1, D0. And if you remember your Karnaugh map, for D2 we form min terms in terms of the input and the present state, and then you put it in the Karnaugh map and try to group them, okay. You can group them only if they are adjacent, okay. So that is what that tells you some rule saying that if you play with the logical adjacency of the states, that might give you an advantage in while grouping, while grouping and basically applying the logical adjacency theorem. If you remember, the adjacency theorem say that AB bar or AB is nothing but A into B or B bar, which is nothing but A, okay. That's what we do in logical adjacency, and that is I am talking about one variable, but that can be applied to any power of 2, like you can apply to 2 variables, then the 4 states are there, it can be possible assignment, then it can be combined to remove the 2 literals in a min terms. So that is what I mean. So aim would be to look for the same next state, since these state bits are output of next state logic, and that is what we want to minimize. So we would like you look for the same next state, we are in a next state table we have input, present state and the next state, and we are trying to optimize the implementation of the next state. So look for the same next state bits. Suppose you are looking at D2, look D2 wherever D2 is 1, or the D2, D1, the Q2, Q1, Q0, wherever there is next state kind of identical, then you can make things adjacent, and for this we would like the min terms adjacent. min term is consisting of input condition and the present state. Okay. So the best bet will be that we have only choice in the state assignment, present state. So we are playing with symbolic state and we are assigning it. Input conditions we have no control. Okay. So it will be good to assume that if for the same next state, if there are same input condition, you make the present state logically adjacent. Then when you group it, some literals will be thrown off from the min term. So we let us look at the same next state with same input condition and make the present state adjacent such that while grouping bits are removed. Okay, that's the basic idea, and this can be done in powers of 2. Okay. So that is what I am going to show. Suppose you have 2 state and I have already done the assignment, but say this is Si, this is Sj, and it is transiting to the same Sk 101. So the rule is that for some 2 symbolic state for the same input condition, they transit to the same next state. What you do is that you make these 2 states Si and Sj logically adjacent. Okay. So this is 0 1 0 0 1 1, it is made adjacent. Then when you group it together when you apply the adjacency theorem, you see that everything else is same but this is differing, so this get knocked off. Okay. So this can be extended to powers of 2. Say you have a 101 here, another 101 here, all the input conditions are same, and hopefully this is like 0 all 0 0 0 0 1. Then you can combine all the 4 and Q1 and Q0 is removed from the equation of D2 and D0 and all that. That's the idea of the heuristics we can apply to the next state logic minimization. So under the same input condition, if the state Si and Sj transit to same next state Sk, make assignment such that the state Si and Sj are logically adjacent, and this is applicable to more than 2 states. Okay. And you can say that it is, even if you can catch on one bit, it is like you say here you look that even if in one bit, suppose this is, you can't get a solution across a bit even for this D2 alone. If you make it adjacent, that is useful, because at least for that there will be reduction in the next state logic for the D2. Okay, that is what I have written here, that state Si and Sj may transit to different next states under different condition, but if both transit to just one next state, it is good enough to make them adjacent. Okay. So like if you can, Si and Sj may transit to different kind of next state at different condition, but Sk, Sl and all that, but even for one Sk, if we can make it adjacent, it is useful. So now you get like the same heuristics can be applied to the output logic. So we are almost kind of, you can straight away tell the rule, the heuristic, that you have 2 present state. Say let us take the Moore kind of output, then the outputs are same, then you just make them adjacent, like you have Si and Sj produces the same output, make them logically adjacent so that when we group, one thing get knocked off. And similarly you have 4 states adjacent, then you make all the 4 logically adjacent, saying that 1 1 1 1 0 1 1 0 0 0 1, so that 2 literals get knocked off the min term. And if it is a melee kind of output, then you have to combine the inputs, you have to make sure that these are logically adjacent for the same kind of input condition, that you have to keep in mind. So that is what is stated here, under the same input condition, that is for melee type. If it is not melee, you can remove this. If state Si and Sj produces same output, make the state assignment such that the state Si and Sj are logically adjacent. Okay. And it is applicable to more than 2 states by powers of 2. There is no point in making, you cannot make 3 logically adjacent, you have to make, say after 2 the thing you have to try is the 4, 8 and so on. And state Si and Sj may produce different output under different input condition, but if both produces even one output same is good enough to make them adjacent as the equation for that output get minimized. What I am saying is that you may not get a chance, suppose you don't get a chance to make kind of all like such a pattern for 2 states, you can look at the subset of these output to do that. I don't know whether the tools do it. Sometime in a simple state machine it may not be worth to try that. I am not sure whether the which synthesis tool try it, maybe at least maybe some advanced synthesis tool like Simplify Pro may try it. I don't know about the recent the Xilinx XST synthesis tool or the synthesis tool of the Vivado. I have not tried it. If I try it I will maybe in the later lectures I will tell you. Now let us come to this kind of issue. So what we have discussed is the state assignment to reduce the area, and we have found that for to evaluate all possible scenarios state assignment and come out with a minimal area is an intractable problem. We have seen the huge computation time required. So then we have come out with some heuristics which is based on some sensible kind of basics, basics of minimization. So it should work, okay. Only thing is that to try and do the next state logic minimization and output logic minimization together may be contradicting, like that you try out the heuristic for next state logic minimization and you come back and try to do again for output logic, both may not work together, that is one problem with that heuristic. If you are lucky it works together. So at least you can try one thing. If you find the next state logic area is much larger than the output logic area, then you can try the heuristics for the next state logic than the output logic. But we are not sure whether we can do it together. It could be contradicting, the heuristics could be contradicting. It may not reap the benefits as you think. So let us come to the next issue, which is something to do with the fault tolerance of the state machine. So this is about the unused state. Suppose we have the number of states as S, okay. Then we know the number of flip flops is n, which is log s to the base 2, the ceiling of that, okay. So there could be unused state because the fact that you end up with a fraction and take ceiling it says that there could be unused state, okay, like here. So the unused state, the all possible assignments the states are 2 raised to n because n flip flops are there. So minus s is the unused state. So if you have states, number of states are 8, then n is a not a fraction. If you take just the log, then n is 3. So in that case 2 raised to 3 minus 8 is 0. But if it is s is 5, so that is the case here, n is 3, then the unused states are 2 raised to 3 minus 5 equal to 3, okay. So the question is that what to do with that, okay. See here I am showing an example of 5 states, this 5 states. So we have 3 unused states and assume that we have done a state assignment like a sequential state assignment. It's a very simple state diagram, and mind you this could be like in most cases there could be simple state diagram like that. Only thing is that there could be kind of self loops here, that could be the only difference from a practical state diagram. So let us, I am not showing all the input transition, but assume something like this, and you have states going through 0, 1, 2, 3 and 4, but 5 are not used, say 5, 6, 7 is not used, okay. And assume that we have not specified this, okay. We have kind of told the tool to treat it as kind of don't care or something like that, And what happens, the state machine is after all some 3 flip flops, okay, and suppose our the circuit FPGA or the chip we are designing is in a noisy environment, okay. It can be some kind of radiated EMI, electromagnetic interference, or conducted EMI. You know that the noise conduct through the supply lines, through the ground, and there was some noisy equipment connected to the same power supply, and some noise gets picked up, either radiated or conducted, and this, suppose this flip flop was in, say, assume that it is in 001, okay. So Q2 is 0, Q1 is 0, Q0 is 1. Suppose the Q2 has flipped from 0 to 1, okay. It was in this state and suddenly it is flipped, this Q2 has flipped from 0 to 1, then the state machine gets into this state 101, okay. Now that, then what happens, the question is what happens, okay. Suppose we have not taken care, we have not explicitly taken care of that in the design, what can happen, okay. So that what all can happen, I mean that is what the first thing. Let us forget about all the technical reasoning. What all can happen, you just as a kind of a creative, or what all possibilities are there, like you can say yes it gets in there, okay, 101, and in the next clock it comes back here, fine, then it is very good, it has gone there and it has come back, then it continues, okay. Or you can say instead of coming back here it comes back here, that could be dangerous depending on the application, because you are doing something very sequentially here, suddenly it skip these 2 steps and go there, it can be very dangerous depending on the application. Now you can imagine this is controlling, suppose the state machine is controlling the radiation of a patient, and this is happen, something initialization is happening, this is the radiation state, and with improper initialization it goes there, what was 5 minutes is becoming 50 minutes, then it's too dangerous, so it depends on the application. Maybe in a simple thing like a vending machine, you ask for the for a soft drink and a potato chips come out, it may not matter, the good for the customer, little loss for the vendor, but may not, nothing life threatening happens, but then it depends on the application. So one possibility is that it can go there and come back somewhere here, and at least for us probably it looks safe than getting it stuck, okay. That is another possibility, you get it, you by noise it goes there and it stays there, like again the clock comes but somehow it stays there. Now we will see what are the chances of it staying there, but suppose it stays there, then it's bad, okay. So if nothing happens it is okay, but if something happens with the data path then it's dangerous, okay. Another possibility is that it may loop through some or all of the unused state, okay. Maybe like after 10 it gets into 101, it comes 111, it comes to 101 and loop, or loop through this whatever way, okay. It cycle through some or all of the unused state. Now assume that this unused state produce some output, okay, some random output, we had some say 5 output, arbitrarily it produces some output, then it can be extremely dangerous, okay. So that is the issue we are looking at it, the fault tolerance. If there are unused state in the state diagram or state machine, and if you have not designed properly and by noise or by some chance it gets into the unused state, it can come back to arbitrary state in the state diagram, it can get stuck there, it can loop through, and if that states produce random output, if you have not taken care, then it can be extremely dangerous. So that is what is stated here. What happens if FSM get into the state, could get stuck there, it could loop through some or all of unused state, it could get back to a valid or used state, okay, it get back to some of the state in the state diagram, and if that state produce some random output then dangerous. So on what conditions above can happen, okay. So we would like to look at in which scenario kind of it gets stuck there. I mean, if you can understand that, maybe it'll at least it is better than thinking like you have such a problem and somehow bring it back to some kind of reasonable state, but how, like in what conditions it goes there and gets stuck, on what condition it could loop through some of the unused state. Let us, at least for an academic curiosity, let us look at it from the basic principle, okay. Now for that to happen, so assume that we have done the next state logic coding here like this. You have process, present state and various input I1, I2, like that, and you say begin and you say k is present state is, and you say when S0, S1, we have 5 states, so you go all the way to when S4, but there is S5 and S6 and S7 and we don't specify that, say we say when others, okay, combining all S5, S6, S7 and all possible kind of states for the simulation, using the standard logic other cases. Then you say next state is don't care. We are hoping that if you say don't care, the next state area is minimized, because we are not explicitly specifying. That means for these S4, S5, S6 you can treat the next state as 1 or 0, and we are hoping that some minimization happen with the proper assignment and the area get minimized. That is why we say next state is don't care, and that also shows the use of that particular don't care, because when we discussed standard U logic and standard logic we said there is something called don't care, and we have not seen it being used, but this is the way it is used, and we are hoping that it gets reduced area. So let us look at one condition, okay, one possible assignment the tool makes, okay. So there you see this is a valid state 000, then 001, and there are a lot of entries up to this ellipsis continuity like 100, okay, which is the kind of S0 to S4 5 valid states, and suppose this is an kind of unused state which is 101, I am showing with a different color, and we say the input condition is don't care, okay, we don't care, and we said the next state is also the don't care, okay. Assume the synthesis tool for optimization purposes treated this as 1, this as 0, this as 1, okay. That means if such a thing happens, by we have written the code like that, and if this is the state, this is the kind of assignment the tool does for optimization, then you see what happens. By mistake the present state become 101 and the next state decoded is 101 itself. From the current present state, irrespective of the input, the next state decoded is 101 itself. So the moment it gets in there, the next clock it transits to the same 101, then it loops through that, and we have not even talked about the output, we don't know, because if you in the output table if you write 101 and say don't care, then the same thing will happen. The tool will assign someone some zeros and all that, and then it will produce some random output which can be extremely dangerous to the application, okay. So that is how this getting stuck happens, and now you can imagine how the loop through can happen, okay. That is what is shown in the next slide. So we have the valid state 0 to 4, S0 to S4, and we write all the valid kind of state diagram, so everything happens. But here for S5, S6 and S7 we said it's all don't care, okay, that is what we have said. Now if the tool do this kind of assignment for whatever reason, for optimization, say 110, 111 and 101, then what happens, you see that if it gets into 101 irrespective of the input condition, the next state is 110. If it get into 110, then the next state is 111, and if it is 111, it is 101. So that is back here. So it loops 101, 110, 111, 101. Okay. Now in this case I have shown all the three. It can loop through the part of the state. Suppose here it was 110 and the 110 comes here, it is back to kind of like 101 become 110, and for 110 it is 101, then it loops through the two states. Okay. So this is quite dangerous, and as I said, we are not sure what outputs are produced by this. Then again the down case and all apply in the output logic table. So it is wise as far as the fault tolerance is concerned to bring it back. Okay. Now when you say bring it back, we have to bring it back to some state, some valid state. Okay, definitely valid state, but in this picture I am showing it to bring it back to the initial state. Okay, but we can only state that bring it back to a safe state. Okay, so that is something which you have to keep in mind. We have to bring it back to some safe state, and in most cases maybe the starting state is good enough. Suppose you take an example of a multiplication, then suppose something goes wrong halfway through the multiplication, then it has gone to this unused state. Nothing happens. The best thing is to bring it to the ready for the next multiplication. Maybe this result is not corrupted, but at least the next one happens properly. But that need not be true for all kind of cases, like you have a state machine, you know, kind of controlling something complex and which takes long time, and it has gone through halfway and you just bring it to the original state. It may not be a good idea. So maybe in the next lecture we will see how to code for this and discuss kind of the scenario a little more, bring a little more clarity to it. So the last thing we have discussed is how to handle the unused state, because if the state machine get into unused state, depending on how you have coded, it can get stuck there or loop through some unused state, or it can come back to arbitrary state, which could be dangerous. So you should bring it back to some kind of safe state, at least for the time being. Let us kind of decide on that, and then we will see maybe more little more detail about that with regard to some applications, and we will continue in the next lecture with the other issues of the state machine. We will try to complete that. So please go back, revise, try to grasp these concepts from the basics, like I have shown some minimization. If you are not kind of forgotten the minimization, please go back and look at it. So though the basics are simple, sometimes knowing the simple thing, connecting it can kind of reap, you will get a lot of benefit out of that than getting stuck with some kind of high level language and try to write some if, then and case with rhyme with no particular grasp and understanding. So that's what I want to say. So I wish you all the best and thank you.